It's a pleasure to have today Markus Linckelmann speaking from London, and he will speak about the Hochschild cohomology.
Thank you very much for the invitation to speak here today. I'd like to talk a little bit about the use of Hochschild cohomology with a particular view towards trying to apply this to block theory. So let me just get right away into it by giving you a bit of background of what Hochschild cohomology is, and then move on from there. So we'll take it for now. A could be any algebra over a commutative ring K, which will later on be a field of prime characteristic. And I'm going to make an assumption, namely that A is projected as K module, which is of course trivial once K is a field. Then what's the Hochschild cohomology? In that case, Hochschild cohomology has a very simple description. It's just an X algebra cohomology of A is denoted by a double H, and it's simply the X algebra of A's itself regarded as a bimodule. That is, A acts on it by left multiplication and A acts on it by right multiplication, which is why I'm putting an opposite here. So this translates the left multiplication into a right multiplication. And so this is a graded commutative algebra. Graded is obvious. Graded commutative is a result due to Gerstenhaber from the 1960s, who was the first person to study this in a systematic way. And as is typical in cohomology, one has nice explicit expressions for the low degree bits of this cohomology. So what is Hochschild cohomology in degree 0? Well, this is simply the same. And I'm writing equal, by which I mean there's a canonical isomorphism between these two things. And similarly for H, the degree 1 bit, these are the derivations on the algebra A modular inner derivations. So what do I mean by derivations? They're derivations. So these are K-linear endomorphisms which satisfy the Leibniz rule. So that f of a product of elements is f of AB plus a times f of B, and that has to hold for all elements A and B. Algebra A, and what are the inner derivations in there? Inner derivations, well, they are those which are obtained by taking commutators, additive commutators with elements in the algebra. So if we fix an element and you define f by taking the additive commutator with this element C, by which element C element say C for all A and A. These are called inner derivations, and it's a tiny little elementary exercise to see that a map that is of this form is always a derivation. You just check the Leibniz rule directly for maps of this type. And but these are not just vector spaces, they're a bit better than that. So the derivations form a Lie algebra. So what's the Lie bracket? So take two derivations and just take the additive commutator in the algebra of linear endomorphisms. So compose F and G, and then take the difference with G composed with F for any two derivations, F and G. One has to again run through a little elementary exercise to show that if you do that with derivations, you end up again in this space of a derivation, and in there, the inner derivations form an ideal. So HH1 is a Lie algebra. If you're working with algebras over the finite dimensional algebras over the complex numbers, then the outer automorphism group is an algebraic group, and this is the tangent space of that. But in parameter characteristic, for instance, it's more complicated. And if K happens to be a field, and I just write characteristic of K is P, assuming K is a field, then the p-fold composition of a derivation with itself is again a derivation. So f to the p, so p-fold composition times is again a derivation. And that turns the derivations, the HH1, into what's called a p-restricted linear. So HH1 becomes p-restricted linear. And although I'll probably be talking mostly about HH1, let me point out that, of course, all of this can be made to work for arbitrary degrees, but it's not entirely trivial. So the Lie algebra structure, or the restricted Lie algebra structure, if we are working characteristic P, extends to H star of A, and so the Lie bracket is called the Gerstenhaber bracket. And one of the reasons why I find this a particularly interesting merit to consider is the fact that this is one of the rare invariants of the stable modular category of a self-injective algebra, at least in a sense that I would like to state. So it's more for philosophical reasons than anything else. But so I'm combining here two theorems, Briggs-Rubio's recent theorem from 21, and then Koenig Liu Zhou from 12, which says that for finite dimensional self-injective algebra, let me just take it over a field of prime characteristic. This graded restricted Lie algebra structure is an invariant under what's called stable equivalence of Morita type. So it's graded restricted Lie algebra is an invariant under stable equivalences of Morita type. What that means is that although you may not be able to read off the stable modular category this graded Lie algebra structure, you know that if you have an equivalence of stable categories which comes from some exact functors of the abelian modular categories living above those, then you do know that such an equivalence will preserve this piece of structure. Now, when it comes to working with, yes, these things there. So if you want to work with group algebras, you have a tool which is going to come up again later, which is called the centralizer decomposition. If you have a finite group, then we have an additive graded decomposition of the Hochschild cohomology of the finite group algebra. That works of an arbitrary commutative ring. You take a direct sum indexed by a set of representatives of the conjugacy class elements in G. And what you take on the right side is the ordinary group cohomology of the central group with coefficients in K additively. And this is as graded K models. Now, you might wonder, okay, but both sides are actually algebras. This left side is a graded X, the right side is direct sums of graded X. So both have graded commutative algebra structures, but they do not coincide. And there's a formula which is due to Ziegler and Witherspoon from the late 1990s, which describes exactly what happens if you want to express the product here in terms of the product there. This is a double coset formula. I'm not going to write down the details. But this is the tool that we have when it comes to calculating Hochschild cohomology of finite groups. Note that in particular in degree 1, this describes the HH1 as the ordinary first degree cohomology of finite groups with coefficients in K. That's just homomorphisms from that finite group into the additive group K. So it's something very elementary and that one can use to calculate this. And as a consequence, we have one thing. So this follows from a theorem from more general work. Linckelmann, Janaszak, and sorry, I forgot Fleischmann to put first here. From 94, that if you have a field of characteristics, if that P lies the order of the finite group G, then the first Hochschild cohomology of that algebra is non-zero. And the way this is done is displayed back to the centralizer decomposition. And in the centralizer decomposition, you have to look at centralizers and you have to basically figure out that you always can find a centralizer which has a non-trivial P subgroup, because that's what it takes on the right side. And because that's a group theoretic fact, well, the way it is proved is it's being reduced back to simple groups, and so proved using the classification of finite simple groups. That's somehow unfortunate. One would think that a totally algebraically expressible fact, like the non-vanishing of HH1 of the finite group algebra, should be something that we should be able to do within that cohomology theory. For now, we have no other way of doing this. And let me squeeze in another theorem of calculations of HH1, which go back a long way. And further, it's with 1930s and Jacobson 1940s. They show that if you have a field of characteristic P and an elementary abelian P group, then the HH1, which is a Lie algebra, this thing, is a simple Lie algebra. I need to introduce one more hypothesis, namely the order of P has to be at least 3. The characteristic can be 2, but the order of P has to be at least 3. And so Witt and Jacobson were interested in, but basically that started off trying to figure out what are the modular simple Lie algebras beyond the classical Lie algebras that gets from characteristic 0 analogs. This was the first case of a Lie algebra that doesn't have a finite dimensional analog in characteristic 0. Okay, so
sorry, Marcus.
yeah.
Did they get like a classification? Did they say exactly which that they classify as simple Lie algebra from?
That's a long and complicated history. So by now, simple Lie algebras in characteristic at least 3 have been classified. there are all sorts of, and for B equals 2, this is still, I think, not done. I think the people who finished it off were Premet and Strade, but there's a lot of work, from the 1960s onwards, by lots of people that has led to classifying these things. So then in characteristic 5, for instance, there's some other family sets that we show, the leaking. So the classification is usually more complicated than the one characteristic 2, but it's essentially done for at least primes for the odd primes.
But not every simple Lie algebra arises as HH1.
No, so that's actually something I'm going to comment on a little later.
Okay.
Yeah.
They're not
3 is not yet classified?
It's 5 and above.
5 and above? Yeah. Okay. I thought there had been some recent advances, but yeah. Just keep an eye on the time. So let me just say a few things of what one would want from the HH1 for be a block of some finite group algebra. And here I'm going to be lazy. I'm going to take this algebraically close of the prime characteristic. So here this is a notation I put in the title. So the very first question, you just phrase it as a conjecture. If B has a non-trivial defect group, well then the analog that what happens to group algebra should happen for block algebras. At least there should be non-zero. So this is an open problem. And unlike in the group algebra case, we don't have a reduction to simple groups here. So everything needs to be done. But in anticipation of the fact that probably the first proof of this, if it's true, is going to go through the classification, people have started to work on this. And for instance, William Murphy, who's a PhD student of mine, started looking at some sporadic groups and found that this conjecture 1 holds for the blocks in any characteristic of the simple macro groups. And he puts a lot more in his theorem, so shortchanging is a little bit, there's a lot of information about the actual Lie algebra structure. Most of these give solvable Lie algebras, not most, but not all. Then, so that's one possible avenue for trying to prove conjecture 1. But here are a couple more conjectures which are more structural, and I'm putting them here. They're not very deep, but they're meant to illustrate what I'm hoping to get out of this. So conjecture 2 is saying that under what circumstances is this a simple Lie algebra? And this, I believe, happens only if B is actually Morita equivalent to one of those elementary abelian group algebras. So the elementary abelian, and all that as before has to be at least 3. In block theory parlance, these are blocks which are nilpotent with elementary abelian defect. And so why am I interested in a conjecture of that type? That's because the condition I'm putting here is something that is invariant under stable equivalence of Morita type. The conclusion contains that this block has only one simple modular. So this would be an access route to one of the big open problems that we have, that we do not know in general how to deduce that, even if we know the stable category of the block, how to deduce what are the number of simple modules of that block. So if we could show that stably equivalent blocks have the same number of simple modules, we would have access to loads of cases of some of the counter conjectures, including Alperin's wave conjecture. So I'm looking for ways into this from the angle of some invariance under stable equivalence of moduli time, telling us something about numbers of simple modules. And very annoyingly, we can prove this for blocks where we know already that is one simple module. Even then you have to work, but this is a theorem that we prove with Rubio, this complete name is really Rossi, in 2018. Conjecture 2 holds if we assume that we have exactly one simple module after its module. And this is, of course, entirely unsatisfactory, because this is precisely what we want to get out of this sort of assumption. And there's another conjecture which I want to write down, which is very easy to write down again, which has a little bit of similar flavor. Conjecture 3. Let's go to the sort of opposite extreme. Here we're talking about simple algebras. Let me talk about one-dimensional algebras. What do I expect for if a block has a one-dimensional algebra? I expect that then this can happen only in the context of what's called blocks with cyclic defect. We can very simply express this by saying that E must be derived equivalent to the semi-direct product of the cyclic group with CP minus 1 acting on it. So this comes from cyclic block theory, that one expects this to happen. But why would this be interesting? Because it's for the same philosophical reason. The one-dimensionality of the HH1 of B, which is there as a root, etc., would tell you that the number of simple modules is P minus 1. And I have to add P off to this. That comes out also of the part of the conjecture. Okay, so this is just to give a very brief motivation, very simple motivation for why I think calculating HH1 is interesting. So far, we don't have enough examples. Actually, we need to calculate more examples. What do these things look like for the finite simple groups, for instance? And I'll come back to that in a moment. But I also want to point out the usefulness of a higher degree part of the Hochschild cohomology when it comes to the rephrasing of some of the numerical conjectures. So, just if this is a short section on Brau's problem 21. What was Brau's problem 21? Brau's problem 21 says that if you fix the number of irreducible characters block, that should bound the size of the defect groups. And so this is a question that Brau asked a long time ago. Does the number of irreducible characters belonging to a block, same notation as before, bound the order of defect? Note that the converse is true because by the famous theorem of Brown and Veit, which says that the defect group does bound the number of irreducible characters in the block. So if this question of Brown's were true, that would just mean that irreducible characters as numbers and the size of defect groups bound each other up to finitely many possibilities. And I should say that there is a nice theorem by Holzhammer and Robinson from 96, which says that this is true if B satisfies the algorithmic time conjecture. And this is proved using a very charming argument making use of Zimmermann's proof of the restricted one-side problem. So, note. Note one thing. The number of irreducible characters in a block is the same as the center of the block algebra, and the center is the degree 0 Hochschild cohomology. Irreducible characters is just the same thing as the dimension of the center, and so that's the same as the dimension of the zeros Hochschild cohomology of B. So what if, instead of just putting in conditions on the dimension of the center, you put in the conditions on the degrees of the Hochschild cohomology? And then there is a way of completely answering both of these conditions, one bounding the other. So this is work with rather Kessler from 2012, which says that, let me just be a bit sloppy the way I'm going to write this down. The order of the defect group and the Hilbert series of the dimensions of Hochschild cohomology they determine each other up to finitely many possibilities. So I hope it's clear what I mean. If you fix a defect group, then you can get only finitely many Hilbert series coming from the Hochschild cohomology of blocks with that defect group. And conversely, if you fix yourself an arbitrary power series, then there can be most finitely many P groups for which there exists a block having that same as the Hochschild cohomology series. So by throwing in the dimensions of all Hochschild cohomology spaces, one can show that these things determine each other up to finitely many possibilities. The proof requires a fair amount of commutative algebra, in particular Peter Simon's proof of Benson's regularity conjectures. So you need to know that group cohomology has regularity 0. And it also needs, one needs to know that if you look at this is the rational function because Hochschild cohomology is finitely generated, so you get a rational function and then can see that the pole at 1 of that thing is the rank of P. So that comes out of some general cohomological considerations which tell you that the curl dimension of Hochschild cohomology is the rank of the defect group. I don't want to go there, just want to say it can be done. And this is one way to rephrase otherwise very difficult questions. And actually, so if you were here 2 weeks ago at this conference and you happened to go to Noelia Rizzo's talk, then you would have seen that there are attempts to nail down blocks which have very few irreducible characters. And this turns out to be an extraordinarily difficult problem, in fact, as you may have seen on that talk, even for very small numbers. So I just wanted to add to this that this can be done if one gives oneself a little bit more information on Hochschild cohomology. So there was this conjecture which was mentioned by Navarro, Zambale, from 2014, which says that
if you have only 3 irreducible parameters in your block, then the defect group must be C3, which particularly forces the characteristic to be 3. And hence, the block itself is Margarita equivalent to either the group algebra or of C3 or the group algebra of S3. So you have these 2 possibilities. And to my knowledge, this is still an open problem. There's quite a bit of progress on this, but the observation I want to just throw in here is that if you give yourself the Hilbert series of the Hochschild cohomology of these 2 algebras, that's going to nail it. So if you give yourself a block and you assume that the Hilbert series of these Hochschild cohomology spaces is one of the Hilbert series of these 2 algebras, so either the Hilbert series of HHN of KC3 TCN, well, if you know that, then you know that your block must be Margarita equivalent to this thing. And the same happens if you give yourself the Hilbert series for the other case. If you know that the Hilbert series of this thing is that of the symmetric group S3, then actually the block is Margarita equivalent to K S3. And it's not difficult to see. But the reason why we can see this very fast is that these Hilbert series are periodic. And that forces the defect group to be cyclic. And then once you know that the defect groups are cyclic, you know, basic, I mean, okay, you have to rule out coterminal as well, but it's very easy to see that they have to be cyclic. And then once you know that, then you know very easily that these are the only 2 cases that can happen. So the remark that I want to make to finish this section is that if you put Brown's problem 21 together with what's known as Donovan's conjecture. Donovan's conjecture is one of those iconic finiteness conjectures, which tells you that given a defect group, there should be only finitely many Margarita equivalence classes with that defect group. Then that tells you that this implies that the number of irreducible parameters, or the dimension of the center of B, which is the same thing, this determines, in particular, the entire Hochschild cohomology up to finitely many possibilities. Of course, the consequence of Donovan's conjecture, because Margarita equivalent blocks have the same Hochschild cohomology algebras. The thing is that that's not a question which is entirely internal to the Hochschild cohomology. So maybe there are ways that allows one to go about this without having to go through some of the finite block theoretic difficult points and difficulties that one encounters. Okay, so this is what I wanted to say about Brow's problem 21. And move on to some calculations. So one thing there's a distinct shortage is actually figuring out what these spaces are, and in fact, with a particular view to the Lie algebra structure, which is even further out of reach. If you think that the non-vanishing HH1 is something that eventually is going to be proved by making use of the classification,
well, then you certainly have to do this non-vanishing for the simple groups, quasi-simple groups. And then if you start with the alternating groups, then you certainly will have to first do this for symmetric groups. So we looked at symmetric groups. And H star in low degrees of symmetric groups algebra, and everything that I'm going to say now in this section is joint work with Benson and Pisser from this year. So, well, we want to do something about the Hochschild cohomology of symmetric groups and see what we can calculate. So we sat down and did some calculations. At first thing we did. So we calculated. Well, we started over the field of two elements of the first Hochschild cohomology space of the and we went up to n equals 10 or something like that. And well, that gave us a sequence of integers, and then we did the same thing with F3, just so that we also have something or some of prime at least. This is not very difficult to calculate by hand. You make use of the centralized decomposition that I mentioned earlier, and cohomology of groups of these centralized. Centralized are very easily understood in the symmetric groups, so this is an easy exercise. But the nice thing that came out was that the online encyclopedia of integer sequences knew about these sequences. So we plugged this into online encyclopedia of integer sequences and got something back in terms of partitions, and then we knew we had a theorem. We just had to prove it. So the theorem is going to be like this. We need for a bit of notation. So let's take n and k positive integers, and if we take a partition, denote by lambda sub k. So lambda sub k is not the length of the sampling lambda. Lambda sub k is the number of parts of the length k in the partition. So in other words, so lambda is, well, the cycle of lengths n appears n times, etc. Then 2 lambda 2 1 factor lambda 1, and of course the sum of the lambda i's times y has to be n. Otherwise, this makes no sense. But so this is the notation for partitions, and then we are going to define f sub k if n to be the total number of parts of length k in all partitions of n. So this is the sum taken over all partitions of n of the number of lambda k. So total number of partitions lengths k of parts of length k in all partitions of n. That's what this number is. And so if k is bigger than n, then this number is obviously 0. And our theorem then says, if we take for p prime and we take a positive integer n, then the dimension over p of the first Hochschild cohomology is equal to, and we have to distinguish the cases where p is 2 and p is odd. For p is 2, we get 2 times f sub n. And we get simply f sub p of n
odd. And once we had this, well, we also sat down and worked out similar but more complicated formulas, which I'm not going to write down, for HH2 and HH3. And the proof uses obviously the centralized decomposition that I mentioned earlier, and a generalization of what is commonly known as Elder's theorem. So there's a bit of combinatorics. This is not difficult. So this has a nicer way reformulation in terms of generating functions. And that makes some other feature here. So generating functions. We get first short bit of notation. So for n plus positive integer, denote by little e of n the number of partitions. So it's a partition function. And let's capital E of t be the generating function, so that's n running from 0 to infinity. With the convention p of 0 is 1. And this has various ways of, you can reformulate this. There's a formula by Euler which tells you how to reformulate this. So the main thing is that this appears in the following theorem, where we try to write down generating functions for the Hilbert series of Hochschild cohomology in low degree. So P is any prime here. For completeness, I'm going to write down also the degree 0 version of this, and there's no surprise here. So if you write down the generating function for the degree 0 Hochschild cohomology of symmetric groups, then what you get is simply the generating function capital P of t. That is true because HH0 is the dimension of the center, is the number of elements in the characters, the number of conjugacy classes, therefore the number of partitions. So this is what we get. So we haven't done anything. But so in degree of 1, the formula looks kind of nice. So what we get here is again, we have to distinguish those two cases. Basically, what we need to write down is generating functions for these functions here. This is not very difficult, and from time 2, we get this extra factor 2. There's no surprise. So what we get is 2 times 2 squared times divided by 1 minus 2 squared, and then we have the E of t is 2, and then we have a similar formula, but with the factor 2 removed, if E is odd. And I'm not going to write this down, but we have this for HH2 as well. There's some formulas I can write down. And I think at some point we got quite far into calculating this also for HH3, and then the formulas became less and less, appealing in some sense, they became complicated. But what they did make us wonder was whether this is not a coincidence, the shape of the answer here, and then the rational function times the partition function. And so we looked at this, and change this again. And we could show the following for P prime, and we need to fix a degree. So R is a non-negative integer. Then there exists a rational function depends on both the prime and the degree in which we are want to calculate things, such that the Hilbert series of the degree R cohomology of the symmetric groups is equal to the product of that rational function and the generating function of the partition function. So from a very philosophical point of view, there is something that has to do with Brown's problem 21. Somehow this formula does tell you sort of that the degree R part exceeds the center, which is encoded by the capital P of t, only by something that is encoded in a rational function. So there is philosophically a connection here. And when we put this out, we got a question. Which came from Ken Ono, which was that is it true that this function R is a function, actually not just in t, but t to the p? And that was a natural question to ask, because if you look at the formulas that we have in our paper on the archive in HH2, it looks like it could be that way. We don't have the answer to this question, so this needs still answering. Okay, so let me just very quickly say I have a few minutes left to mention what are the main ingredients that go into all of this. So the main ingredients. Without any surprise, it's the centralized decompositions. That's always the first thing when you try to figure out dimensions of Hochschild cohomology spaces of group algebras. In this case, what you get is interesting, because we can calculate centralizers of elements in symmetric groups very explicitly. Those centralizers are themselves direct products of some Ries products, and then you can, when you take cohomology of that, you can get that as a Künitz formula. So you get actually a very neat explicit formula for the centralizer decomposition, which is like this. So the direct sum has to be indexed by the conjugacy classes of elements, that is partitions of n, and then the centralizer being a direct product of groups that translates into a tensor product of the cohomology spaces corresponding to the various bits of the centralizer corresponding to the parts of the partition, and this is looks always like this. These are always Ries products. It's just the nature of the centralizers there for the cohomology to begin.
formula. And then there is this is one ingredient. Then there's another key ingredient, which is work of Nakamura from 1961 in the Annals, which is a stability result on cohomology of symmetric groups. So Nakamura studied the cohomology of the infinite symmetric group being the colimit of the finite symmetric groups, and realized that in every fixed degree, as you go to infinity with the degree of the symmetric groups, the cohomology becomes eventually constant. And so this is a key ingredient, stability results for the cohomology of finite groups. This plays quite a role actually in various bits of algebraic topology. Some algebraic topologists are interested in these stability results. And then the last ingredient is, which was fun, some elementary graph theory. That comes into play because if you look at the Scribner's formula, then you have to read the gradings of these things correctly. So it's a tensor product of graded things. So you have to compare this to the grading on the left side by taking the total degrees in these tensor products. So that's quite messy. And there's a bit of graph theory which does that. Let me just write down for fun the one formula that we needed. But if you take the sum over some y, so we'll say in a moment what these symbols mean. Minus 1 to r, then factorial, sorry, where y runs over the simple and undirected graphs on r vertices, where E of y is the number of edges, and C of y is the number of connected components of y, and one puts this quantity which plays a role in unraveling this formula on the right side. Okay, so these are the three ingredients. I'm not going to give more detail. Combinatorics is always hard to read, so let me leave it at that. To finish, yes.
Sorry, what's the simple?
A simple graph is just it has no loops and has no double edges.
Oh.
Yeah, and it's undirected. So you just take any set of edges from these other vertices, and yeah, the right side shows up as the chromatic polynomial, as the complete graph evaluated at -1. So there's a bit of fun facts in the background. Okay, so what we couldn't answer completely was even this question that I mentioned earlier, whether for any block of a symmetric group algebra with non-trivial defect, the HH1 has to be non-zero. And using Chuang-Ruqian, one can bring this back to a question of principal blocks, because derived blocks have the same HH1. And that's good enough for cracking it at the prime 2. So if E is 2, then any non-simple, let me just say, block B of symmetric group, doesn't matter on which field of characteristic to as non-zero H1. We don't know this. We don't know this when P is odd, despite the fact that it's clear that its cohomology spaces, they grow so rapidly that they would be very unreasonable for the block to produce a zero HH1. Structurally speaking, we have another question. This is really a question, actually. We've worked on the dimensions of these spaces, but actually, we would really like to know more about the
the Lie algebra structure, and I have a suspicion that these Lie algebras of the symmetric bundles are they always solvable? So this is another thing that we couldn't do. And once you've done all of this, of course, then the next question comes, well, do we start with the alternating groups, other coefficient groups, the algebras, then the GLNs, etc., and see wherever you have a combinatoric that would allow you to run through a similar program. Okay, thank you.
Maybe you kind of answered it at the end, but when you wrote this formula down at the top of this dashboard, it looks like the natural question would be what it does to blocks. Like you've got something labeled by partitions on the right hand side, so you can look at the chords, and there's nothing like that. There's no correspondence.
No, so the general problem that one has with all of this is that even for symmetric groups, the centralizer decomposition is not well behaved with respect to the block decomposition. So you can't take chunks of the centralizer decomposition and assign them to blocks. It just doesn't work. And so this is actually something that's really missing in the theory. Find a way to make the centralizer decomposition maybe a bit coarser, but then compatible with block decomposition. So this is a real problem.
So do you even know, you wrote some conjecture down earlier about if you have non-trivial defects, it was something is much earlier in the talk.
Yeah.
Do you even know this for the symmetry?
No, we don't. That's the HH1 being non-zero was this thing. We know this from equals 2, but we don't know it when yeah. So yes, that conjecture is even not in this curiously. And should be within reach, but
you have another question? Presumably these capital R's, I think maybe on the board above, maybe it's just covered up the rational functions.
yeah.
Presumably it's very sort of non-constructive.
So the way it is proved would allow you to write them down. You probably could write a computer program to them.
It's like an iterative thing. So
yeah.
Well, you would need the dimensions, low-dimensional cohomology groups.
Yeah.
Yeah. Dimensions of the cohomology.
Yeah. Yeah. But I mean, all of that is probably, you can probably plug this into a computer.
I mean, if you have those formulas.
Yeah, just because the stability result,
yeah.
You know that.
I don't see anyone in the chat, so I would suggest choosing the speaker area.